All right, so now I'm going to take a look at another example of graphing a quadratic function. In this case, we'll graph y equals 2x squared. But what we'll always do is compare every graph to what I refer to as the parent graph, y is equal to x squared. And then for y equals 2x squared, we want to figure out the vertex, whether the graph opens up or down, and then write an equation for the axis of symmetry. So here's the first thing I'm going to do. For this equation, kind of like the equation y equals x squared, I'm going to create a table. So I actually started to create the same table I did as for y equals x squared, but now I want to graph y equals 2x squared. If I'm doing everything in my head or you're trying to figure things out in your head here, you have to use the order of operations. So here's the first input, -3. Then your equation would look like this, y equals 2 times -3 squared. So you have to do exponents before multiplication. -3 squared is 9, and then times 2 is 18. And I substitute in -2, y equals 2 times -2 squared. -2 squared, again, exponents come first, is 4. So then it's 2 times 4, which is 8. And for y equals 2 times -1 squared, -1 squared is 1, times 2 is 2. Y equals 2 times 0 squared, 0 squared is 0, times 2 is 0. And then you might be able to figure out pretty easily in your head what happens when x is 1. So it's 2 times 1 squared. 1 squared is 1, just like we had here. And then times 2 is 2. 2 squared is 4. And then times 2 is 8. 3 squared is 9. Times 2 is 18. So now I'm going to graph all those points. So the first point, -3, 18, it's going to kind of go way off my graph. So I'm going to leave that alone right now and actually not put it on my graph. -2, 8 is right here. -1, 2, 0, 0, 1, 2, 2, 8, and then 3, 18 going to be kind of way up there. So I'll just leave that alone. Here's the graph, and I'm going to kind of color coordinate things. Again, it's a parabola. Notice how I made it a U shape. Everything is curved, but this is y equals 2x squared. Since we want to compare it to y equals x squared, if you remember for y equals x squared, our table looked like this. X, Y, -3, -2, -1, 0, 1, 2, and 3. I did the work earlier, 9, 4, 1, 0, 1, 4, and 9. But I'm going to graph all those points. 2, 4, 2, 4, and then I could actually fit 3, 9 on the graph and -3, 9. And the graph looks like this. And then it said compare it to the graph of y equals x squared. So what I'm doing right now is comparing the red graph, y equals 2x squared, to the black graph, y is equal to x squared. And to compare it, for y equals 2x squared, what actually happens, the graph gets skinnier. That's what's known as a vertical stretch. The graph is, again, skinnier, specifically by a factor of, or sometimes I'll just abbreviate that, BAFO or BAFO is by a factor of, in this case, 2, because A is 2. So the graph gets skinnier, and then specifically it's skinnier by a factor of 2. That's comparing it to the graph of y equals x squared. So what I'm looking at right now, again, the red graph, the vertex is right here. The vertex is at 0, 0. That's what it means to name the vertex, tell where the vertex is. Whether the graph opens up or down, it's a regular U, so the graph opens up. You'll see for other examples where the graph would open down, and then write an equation for the axis of symmetry. So the axis of symmetry for actually both of the graphs, right down the middle, is right here. It's the y-axis, but the actual equation for the axis of symmetry, or again, it could also be referred to as the line of symmetry, is x equals 0. So x equals 0 is actually the y-axis. Again, the axis of symmetry really should always contain the vertex, but that's a graph of y is equal to 2x squared.